This is lesson 19, and it has to do with transistors still, but it's a different kind. It's called a field effect transistor, abbreviated FET, or you just call it FET. There are a number of these, and there are a couple of different major varieties. The one that we're going to do is called a MOSFET. It is a metal oxide semiconducting field effect transistor. And this is not one that he has very much in the book about because, well, not because, but he has a different kind. But when I went to find some of these, the MOSFET was the one that I could actually find and send to you. It turns out that in a later chapter, in chapter 10, he has a diagram of one, but I'm going to go ahead and draw the diagram here and talk just a little bit about it. So on page 159, down at the bottom, there's not a lot of space, but because of the spacing for the rest of the things, I decided that this is enough space to do what we want to do. So a field effect transistor is arranged a lot different than the bipolar junction transistor. Those are based on the concept of two diodes. Now, you cannot just take two diodes and hook them together and have it to work like the transistor. They're built a certain way, but this one is built quite a bit differently. It still depends, though, on N-type and P-type semiconductors. So I'm going to draw this on the board, and then you should sort of draw most of this on page 159. So there's a MOSFET diagram. So we're going to start with a line, and then we're going to put a dot here and a dot here. This is going to be called the source. Now, we had the base and emitter and collector on the other transistor. On this one, we have what's called a source and a drain and a gate. So there's a region of material where the source wire is connected, and this is N-type. And then we have a space over here, and then we have another region, and this is also N-type, and this is called the drain. Okay. Now, when these are manufactured, these are extremely small. And I believe it was in one of the other lessons, or actually in a footnote, he said that there's a little over 3 million transistors in one silicon chip. So when they manufacture these, a lot of times they can manufacture them with only like a layer of atoms, or a very few layers of atoms, and so they're not really big things. Okay, so if these two are N-type materials, then we need to have some P-type material down here. Okay. The next thing we're going to do is we're going to put an insulator. And this is the insulator. We're also going to put some insulator over here and over here, although I'm not going to write the words. Okay. Then on top of this insulator, we're going to put a metal. Okay. And from this, we're going to put a wire up, and this is called the gate. Okay. So the problem is, how do we get any current going anywhere in all of this? I might add that there's a diagram, the diagram that I just mentioned is on page 134. Okay. So what happens though is if you apply a potential difference to the gate and to the other side of this layer, you can get this metal to become positive. So you apply potential difference properly, and electrons will leave that metal. Well, if it becomes positively charged because electrons left, then that will attract electrons in this region under here. Now they can't travel through the insulator, and that's the whole point, but they're attracted into that vicinity. So what happens is we get electrons collecting in this region. And when electrons collect in this region, and then we have the electrons, the available electrons in the two N-type materials, then this becomes what's called a conducting channel. And then you can have current. So I think at the moment that's all I'm going to do with this. It's very complicated as to exactly what happens, and it's one of those things that you really need to either know the whole story or just a tiny bit. If you know about half of the story, then it's very confusing. So I decided that we would just know a little bit. And the basic idea is you have an insulator here, a metal here, you apply a potential difference, the metal becomes net positively charged because electrons left. That will attract electrons from this material into this region, and then the two N-type regions along with this channel here, then that becomes conducting. And so then you can have current. Okay, the next thing we're going to look at is circuit symbol. I'm going to show you actually both types because this one is an N-channel. This is called an N-channel transistor because of the N's here. Now, you can reverse this and put P-type material here and N-type material here, and then it works basically the opposite. Many of these, the FETs are N-channel transistors, so that's why I showed you that one. And that's the only diagram that you need to know as far as how the transistor works there. So we're going to look at how these are labeled, and I will show you both of them. Didn't leave much space there, but you can probably get both of these here. This is the drain, this is the source, and this is the gate. Now why they put the gate going there with the source, I don't know, but that's the standard notation. And this is the direction of current, and this is the N channel. Now, we can do the same sort of thing, and if you remember with the transistors, or with the other ones, where we had the base and the emitter and the collector, it depended if you had an NPN or a PNP, and the current was labeled one direction in one and the other direction in the other. So that's what happens here. So we're going to have this, and we have the drain over here, we have the source over here, we still have the gate in the same position, but the arrow is the other direction, and this is for a P channel. Okay. Now, the last thing there in that little space that's left is characteristic curves, and that's an important feature because that's what we're going to look at. We're only going to look at part of one of those, and I will explain kind of what we're going to do, and we will look at a circuit. But the reason that we're limited is because of the particular transistor that we have and with what the circuit board will will produce. So the characteristic curves, and you actually did this with the diode, except I didn't have you doing more than one. If you remember the first lesson about the diodes, or one of those lessons with the diodes, you had voltage and current, and you got a current voltage graph for several different kinds of diodes. So what we're going to do here is just see what the general idea is. The general idea is that we're going to have current, and this is actually the drain current. So it's the current from the drain. And I'm going to draw this a particular way so that I can get it the way that I want it, or the way that it should be. Oh, let's just put one more there. Okay. So what happens is this is the voltage, the drain source voltage. Okay, so the potential difference between the drain and the source, which would be the drain and the source. Now, each of these different lines goes with a particular gate source voltage. So, if you remember I said when you apply potential difference between the gate, actually it must be over here to the source, and then once you apply that, we're going to call that V gate source. You apply that and keep that constant, and then you change the drain source voltage and you monitor what the drain current is. So this may be positive, like 5 volts, which is what we're going to use, or 10, or 4, or 5, or 6, that sort of thing. It also depends on whether you have an N-channel transistor or a P-channel, and I believe that the N-channel, these are positive voltages, and for the P-channel they might be negative voltages. So the important thing is, though, that we're going to look at a positive gate source voltage. We're going to vary the drain source and monitor the drain current. Now, the problem is that when I did this, and I was very good about this and did the experiment before I wrote it all up, I found that nothing that I was doing gave me a flat region here. All I could get was a linear region. So I decided, well, let's go to the internet. I have been somewhat successful from time to time, although I don't feel like I'm nearly as successful as a lot of students are. But I looked up this particular transistor, and I'll just put it down here. You don't really need to remember that. It's an IRF510 MOSFET. Okay, so I typed that in, looked it up, and found a bunch of different things, found a lot of stuff about it. And I think I actually typed in characteristic curves for this, and I finally found a set of characteristic curves for this particular transistor. And in the lesson, I have given you the website for that. It might be good if you look at that. There's a set of, I don't know, it's about 7 or 8 pages, but I think it's page 4 in the upper right-hand corner. There is a set of characteristic curves, exactly what I was looking for. So after I looked at it, I realized that over about here or so is 10 volts, and up about here or so is 2 amps. Okay, now 2 amps, not milliamps. 2 amps is a lot. However, when I was doing the experiment, the voltage between the drain and the source was no ways near 10 volts. In fact, it was on the order of millivolts. And the current I was getting was milliamps. So based on that, I realized that the data that I was getting was in this little region here, this linear region. I was not able to get into the flat region. So I thought, well, what can we do with that? So I decided I Xeroxed this and I enlarged it a lot. I don't have these on, they're not that easy to post, but I don't know, you can kind of see, this is what we have. So I looked in this little region down here. I measured very carefully with millimeters and I found the slope of this line. Okay? So I decided what I would have you to do is collect data. You can plot a graph and you can find a slope for this line here, this little region, and see how well it compares to what I had, what I calculated based on the graphs that I found on the internet. And from what I did, mine matched reasonably well. So at least there's hope. Okay, so now, the next thing I need to do is on page 160, I want to show you the circuit that you're going to build. I'm also going to show you one of these transistors. So I need to erase some things here. I'm going to leave that. And I'm going to pull out my transistor. So we'll show you a little bit, another close-up after when I put it back in the circuit. But it's a little black thing, and I think most of you, if I send it to you, you've seen what it is. It's a little black thing. It has a silver top, and the silver is also on the back. That's a heat sink, and then it has the 3 legs. So what I'm going to do is on the board, I'm going to draw a diagram of this and then a circuit diagram. The circuit diagram is sort of like the one in the book, but it's a little bit different. Okay? So on page 160, you have a lot of space. So on the left side, you should actually draw the diagram of the transistor. So we're going to have it with the black side up, and then there's this other little part that you hold on to. This is silver, and then there's the 3 legs coming out, and the top one is the source, the middle one is the drain, and the bottom one is the gate. Now, when you're putting this in the circuit, it seems to me it would have been a lot nicer if they'd have been a little bit differently arranged, but that's the way they are. Okay, so we're going to look at our circuit. I'm going to start by drawing the transistor. So we have the source, we have the gate with the arrow in, and this source is going to ground, and this is the GND, the black ground in the upper right hand corner, and this is the drain. So we're going to have this to go up here. We're going to measure the drain source voltage, so we eventually want our voltmeter from the drain to the source. And this side will be black, and this is going to measure, this side's negative, this is going to measure the drain source voltage. Okay? Now, up here from the drain, we have to have a positive voltage. So we put a resistor in there, and I'm going to call this the drain resistor. It's 1 kilo ohm, and that is brown, black, red. Okay. Then if we're going to measure current, we need to have an ammeter. So we're going to put our ammeter in here. The negative side here, the positive side there, and then this goes up to the positive 15 volts, which is the yellow terminal. And I'll show you that on the circuit board in just a minute. And so from this, we're going to end up with the current drain. Now, this side over here is our gate source voltage, and that's going to be our positive 5 volts, which is the red terminal. It's the constant or the fixed 5 volts. And on our circuit board, that's the only fixed one that we have there. So we're going to get part of a graph here, and if we could have the drain source voltage large enough, then it would level off. But we can't get into that region with our equipment. Okay? So this is our gate source voltage, a constant 5 volts. Our drain source voltage, which we're going to vary, and as we vary this potential difference, then the current will vary. And then this is connected to the positive 15 volts. This is the variable voltage, so we can change this. It turns out, though, that the 15 volts is up here, here to ground, and for our graph, we need from the drain to the source. Okay, so that's the circuit you need to draw on page 160. And now we're going to go to the circuit board, and I'm going to show you, oh, I need my papers. I need to put this back in. And if you notice, I said that you need to insert it with the black side to the right. And I hope I think that's where it was. Okay. So now, oh, I need the rest of my instructions. Okay, here we go. Okay. So we generally start with things turned off. That's the best way to do it. We have the transistor that we put in here. The gate is the bottom wire, and it goes connected to the 5 volts fixed, which is here. So what I've done with this wire is I have brought it around this direction instead of around the other way. I originally had it the other way, but then it was getting mixed up with this other terminal here. So I've got it around this direction. The source wire, which is the top one, needs to go to the ground. So I've got a wire in where the top wire is, and it goes up here to the ground. The drain is the middle wire, and it goes to the resistor, so I've got that connected back there. And the other end of the resistor just inserted into the circuit board. And then we're going to, let's see, we're going to measure current. So we need to go from here, and we're going to use our yellow meter, and we're going to set it at 200 milliamps. So it'll be 200 milliamps. I'll just go ahead and turn that on. It's DC, so actually I'm not sure if this has AC current. I don't think it actually does. So that's all right. Then, let's see. Then the red lead of this needs to go into our positive 15 volt terminal, which is up here, the yellow terminal. And if you've had the alligator clips on here, you can just use the alligator clip there, or you can just take it off and just put that in there like that. Now at this point, it's a good idea to turn this positive voltage control knob down so that you've got low voltage. And at this point you can turn it on, so I'll turn it on. And generally you should sort of notice, do you see any smoke or anything like that? If you do, turn it off immediately. As you go through this, and actually the next circuit, It's a good idea, kind of put your hand over it, and if it feels really hot, then you should turn things off. So far I did that actually with one of the op amps in the next lab, but that means it's not working right. Okay, so now the orange DMM, which I've got over here, we're going to use it to measure the drain source voltage. The red lead goes in that hole and then to the drain, and the drain, remember, is the middle wire. Right, which is where my resistor is connected. And then the black lead here goes to this black ground up here. So again, you could use the alligator clip or just take it off and put that in there. Okay. Now, somewhere in here, I think I said that you have to have the, which is this, the source. Yeah, that was in actually part C, connected to the ground up here. One thing that I wanted to, a comment I wanted to make is when you're putting these wires in here, you want to make sure that the insulated part is not getting under there, because if you do, it will not make good contact and you'll wonder why things aren't working. And I found that out from experience. So it's always a good idea if you can still see just a little bit of the stripped part when you're putting those into there. Okay, let's turn this on. Oh, this should be on 200 millivolts. It doesn't hurt if you have it on higher, except you won't get any numbers. So I'm going to turn that on. Notice it's already 0.9 and this is 1.3. So as I turn this knob up, you get a little bit higher voltage there and you get more current here. And I don't think that you're in any danger of burning out the fuse on this, because as you turn this up, I think about the highest it will go is like 14 millivolts. So doesn't seem to be getting hot. But once you get your highest number, I think I only said to go to 12, but if you want to go on up to 14, that's fine. But as soon as you get your data, then you should turn that knob back down. Okay, at that point, then you're going to plot a graph. Now, you'll end up with units of amps over volts, which as far as I know, well, it might actually be something. But since we're going to compare it to the slope of our characteristic curve from the internet, we'll just leave it as amps per volt. And then there's a question there, a little bit of information about the characteristic curves. And then I think that's the end of the lab. Then there's a few questions.